engine is considered to be an ideal engine. Many a times, if you want to study the difficult concept or what actually happens in reality, first we have to understand what happens for an ideal system. So ideal system means in this case it will basically go back to the same point from where it actually started. Okay, and whenever we are basically going to talk about engine, we need maximum efficiency. Efficiency is something which is in terms of percentage, like an engine can be 100% efficient, which is actually not possible. That is only an ideal case. So efficiency will be in terms of percentage, or you can take it as a value from 0 to 1. So if I say it's 1, it's 100% efficient and so on. So if you basically consider an idealized system, thermodynamic system rather, that will actually be based on something which you call as Carnot cycle. So there is a very simple diagram based on which we can actually understand this. But before we go to that, we are going to just look into the cycle. So there are four processes in a cycle. Okay? There are four processes in a cycle, and for this what we can do is we can actually consider similarly whatever we have done, a box, okay, or a cylinder which is actually having some kind of gas, and basically it has got a piston attached to it. Okay, and in a Carnot cycle there will be two expansion cycle and two compression cycle. And at two places we are going to expand, and at two places we are going to compress. Okay, so in terms of work done, in two places is going to be positive work done, in two places is going to be negative work done. So we'll start with isothermal expansion. Okay, so what happens is the gas will expand here. Okay, we have the gas inside, and this gas will actually expand. Okay, and isothermal money we are going to keep the temperature constant. Okay, so what happens is we basically have a heat that is getting absorbed, because of which the gas will actually expand. So that means this is positive work done, because work is done on the piston and this is expanding, so work is done by the gas, positive. Next we have got adiabatic expansion. Adiabatic expansion also the same thing. There will be further expansion, okay, of the gas, but there is no exchange of heat. Now what happens is, if there is no exchange of heat, let's say we are going to consider a very small region where the heat cannot escape the system but it is expanding. So that means in order to conserve energy, if that expansion takes place, the temperature will drop. Okay, the temperature is going to drop. So this is what happens in adiabatic expansion. The gas will expand, there is no heat coming from outside or escaping from inside, so that means the temperature has to drop. So this is the adiabatic expansion. So whenever there is an adiabatic expansion, there will be a change in internal energy, and as we said, if temperature changes, internal energy will change. My internal energy will be more if temperature is changing more, and the change in internal energy would be less if the temperature is reducing. So here it is reducing the temperature, so the internal energy decreases. You can also think about it in this way. If you're basically having a very small box and there are so many gases molecules inside, it will have some internal energy, kinetic energy plus potential energy. What you do is suddenly you expand the size of the box, but you don't allow any heat to come from outside. The number of gas molecule also remains the same. That means the gas molecule now have more space, so that means its kinetic energy and the potential energy is going to reduce. Potential energy, so you understand, if you have basically let's say this is something there and you have a spring in between, this spring is pushing it. Now if you all of a sudden expand this and bring it here, the spring will push lesser, that means the potential energy is reduced. Similar thing happens here also, the potential energy will drop. Potential energy drop, kinetic energy drop, internal energy will decrease, and this will only happen when the temperature reduces. So this is adiabatic expansion. The third process is isothermal compression, and compression means we are going to do the work on the gas, not the gas is not going to do any work. In fact, what I'm going to do is I'm going to take this piston and I'm going to push it down. But and here also there is no heat which is no, this is isothermal, so there is no temperature that is going to change. Okay, the gas is compressed isothermally at lower temperature, right? So it was it has, after expansion it has gone from TH to TL. Now I'm going to keep the temperature same TL, but then I'm going to compress the gas. Now if I'm compressing the gas but I'm going to keep the temperature lower, that means the system has to give out some heat, and that's quite obvious. Let's assume that the temperature of the gas is 120 degrees centigrade. Now I want to keep it at 120 degrees centigrade, but I'm compressing the gas. Now naturally what happens is, if I'm compressing the gas and I'm not allowing the heat to escape, the temperature will increase because the gas molecule will start colliding more. So that means the temperature should increase, but I want to keep it constant. So that means whatever extra heat is generated is going to get escape, and that will escape into the cold reservoir. So cold reservoir means you are having a system, let's say a thermos flask or a cup of tea. The cold reservoir will go into the environment, into the air. So that air or environment is acting as a cold reservoir. So cold reservoir is not something that you maybe need to construct specially. Okay, you can just keep it like this. Okay, so that's important. So, and the final expression is for adiabatic compression. So we have talked about the three process, and the final one is adiabatic compression. Now, adiabatic compression, it means that I will basically have the same thing here. I'm going to compress the gas further, but then I'm not going to allow any heat to escape. Now I'm compressing. The temperature will rise because I'm compressing it, and I'm not allowing the heat to escape. Heat is not escaping. That means it's quite obvious that its temperature will actually rise. Okay, so the temperature will rise. So these are the four processes that is actually taking place in a Carnot cycle. Okay, before I go to the efficiency of Carnot cycle, let's just look into the diagram. Okay, since I'm going to publish it in YouTube, and I've taken this diagram from Web Byju's, so I'm just acknowledging this. But this diagram more or less explains everything. If you want to plot a graph between pressure and volume for a Carnot cycle, we are going to have these four positions. The first one is we are going to have a pressure P1, a volume V1, and let's say temperature T1. Okay, let's say temperature T1. I'll just write it here itself. Now I am going to expand the gas isothermally. That means if the temperature is T1, it is going to remain as T1. It is going to remain as T1 here also. Isothermally, when the temperature is constant, right? So what happens is, if I expand this, obviously the volume will increase. So you see, this is the volume V1. This is my volume V1, and the volume has increased to V2. Quite obvious, because I'm looking into the x-axis, the volume is increased to V2. This is expansion, right? Now if it is expanding, the pressure will also change, because what happens is volume and pressure are inversely related, right? PV is equal to nRT, or if we say isothermal process, this entire term is a constant. So that means pressure is inversely proportional to volume, and that's quite obvious. If I take a balloon, and if I'm going to expand this and I'm not going to introduce any new gas molecules, that means the pressure will drop. So here the pressure reduces, and that's quite obvious. Here we are basically having pressure as P1 in the diagram, and then when I'm reducing the pressure, this will become P2, pressure P2, and P2 is less than P1. You can see it from the image. Next, adiabatic expansion, we are going to expand it again, but this time the temperature is going to change. Okay, this temperature is going to change. So because it's adiabatic, I cannot have the heat escape the system, so the temperature will change. So that means the temperature will become here T2. So this is for the expansion case. Here also expansion, the volume is going to expand further, it's going to become V3, and the pressure is going to reduce further, so the pressure will become P3. Now we'll come to compression. So when we go for isothermal compression, we are going back here. That means the volume will reduce now. So let's say it's V4, and we can see it's going from V3 to V4. So that means the volume is not more, it's less in fact, right? V4 is less than V3. You can see it from there. अगर volume कम हो गया तो मतलब pressure बढ़ गया, so pressure will be more. So pressure will be more P4. If you take a balloon, you try to squeeze it, that means you are reducing the volume, but then the pressure will increase. Obviously the gas molecules will exert more pressure. So this is what is happening here, but it is again an isothermal process, so the temperature will remain as T2. Cyclic money is going to go back to A. That means again when I am going to do the adiabatic compression now, not expansion, compression, we are going to get back the same volume V1, and V1 is less than V4. The pressure is going to go to the top now, P1. So P4 and P1, huge gap. So you can see the pressure is increased very much, P1, and the temperature will get back to T1, okay, original temperature. So this is called Carnot cycle. Why cycle? Because it's going to get back to the same situation or same scenario. So this is a very important thing. This is theoretical. Whatever we have said, we have explained what are the four cycles: isothermal, adiabatic, expansion, isothermal, adiabatic, compression, four cycles, and we have to draw this diagram and explain the things whatever I have written in the previous part. Okay, so based on this, we basically have the Carnot theorem, but we'll come to that later. Based on this, we can actually find out a lot of relation again. The first thing is more or less what we call as efficiency. Efficiency is more or less output divided by input. Now let's say we have got the two temperatures, okay. It is initially TH, okay, but it drops to TL. So T is the, let's say, the temperature of the cold reservoir, TH is the temperature of the hot reservoir, okay. So what happens is whenever we are going to write down efficiency is nothing but for anything, okay, not only for Carnot cycle, for whatever. In electronics also, if you are going to find out the efficiency of any circuit, you always need to find out what is the output divided by input. It is always output divided by input. So input is whatever was the temperature originally. So original temperature was TH, temperature of the hot reservoir, the point at which you start, okay. And output is nothing but whatever was the temperature of the heat reservoir minus whatever heat is rejected. That means whatever heat is given out to the cold reservoir. So that is my output, right? This much is the used temperature. This was the original temperature. Now you can separate it out. TH by TH will become 1 minus this will become TL divided by TH. So this is a very important form of efficiency. Sometimes they do ask you questions from this as well. So this is very important, okay. Next is work done. Now you see work done is very interesting here. What happens is work done is the combination of all the four processes. You've got isothermal expansion, isothermal compression, adiabatic expansion, adiabatic compression, okay. So you can add the work done in all the four processes and find out the final work done, okay. So it is basically nothing but, if you want to understand what is the work done, whatever heat is being absorbed and whatever heat is rejected to the cold reservoir, the remaining heat is used to do the work, okay. You take some heat from the hot reservoir, that is QH, and then you reject the heat to the cold reservoir, which is actually not used, and whatever is left is actually nothing but the work done. So this is a very simple and straightforward relation that we can actually use to find out the work done. So the process is reversible, okay. So if there is a ratio between the temperature and heat are directly connected, we already know it, because we know that this Q is directly related with temperature, okay. More temperature more heat, less temperature less heat, so direct proportional. So when I am যদি বলি there is a ratio between temperature given to the cold reservoir divided by the temperature of the hot reservoir, the same is the ratio between QL by QH. So many a times this relation is needed, because you might get some question where three parameters are given and you are supposed to find out the fourth one. Let's say I'm giving a heat to a system whose this much joule of heat, okay, and the temperature of the hot reservoir is this, and then the temperature which is given to the cold reservoir is given some value. You have to find out what is the loss in heat. So you can use this relation and directly find it out, okay. So heat and temperature are directly connected, okay. So when we talk about the Carnot engine, we have to assume certain things, which is important because it's basically an ideal engine. The working substance undergoes only reversible process, which is actually not a fact when we are considering an ideal system, a non-ideal or a real system, okay. This is an ideal system, so the working temperature undergoes only reversible process. This is the first thing. There is no friction or dissipative forces. That's quite obvious. Basically what happens is, if it wants to go back to the same point, original point, there should not be any loss. If there is any loss, it cannot go back to the original point. But if there is friction or dissipative force, there will be loss, so it definitely cannot go to the original point. So that is the idea here, that friction and dissipative forces should not be there. That is the assumption that we are doing. So what happens is, basically in a steam engine and all, The efficiency is not 100% because you cannot avoid friction, dissipative forces. If you take talk about a car engine, that also eventually dies off, right? At some point of time it will lose all its efficiency. Okay, so these things are there because of friction. So this is something which is not ideal. Heat transfer only occurs between working substance and reservoir. Again, something which is there, working substance and the reservoir. It's not considering if there is any heat loss within the system and so on. Okay, engine operates between two thermal reservoirs. That means the cold reservoir and the hot reservoir. Hot reservoir is supplying the heat. Cold reservoir is getting the rejected heat. Okay, the rejected heat is sent to the cold reservoir. So that is very important. So significance, I'm not going to explain. It's quite simple. Like it's basically giving you an idea about efficiency. That if you're basically making an engine or designing an engine, it should be as efficient as a Carnot engine. So if it is closer to the efficiency of Carnot engine, that means it is basically a good engine, right? So that is what benchmark is meant. Second law of thermodynamics, entirely based on second law of thermodynamics, because we are talking about the work done in different cycle and process. Okay, and then it is reversibility. Okay, something which is reversible we can understand from the Carnot cycle. Okay, and limitations is quite obvious. Carnot engine are idealized, and it cannot be realized in practice. Okay, because you cannot have something which is 100% reversible. You're definitely not going to get that system. Okay, and this is very important. Sometimes we miss this. This is actually a quasi static process. Quasi means uh, static means it's static, it's not moving from one point to another. Quasi means it's a misnomer, means it looks like it is static but it is actually not static. So in general, quasi means it's going to go from one point to another very very slowly, from A to B very very slowly. So if you're going to have an adiabatic expansion or isothermal expansion, it's not that you're straight going to pull the pulley very fast. That's wrong. Okay, you have to pull it very 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 slowly, and that is the idea of quasi-static process. So any thermodynamic process which is ideal in nature is more or less on paper quasi-static in nature. It's going to be very very slow. Okay, uh, in exams, if you do it, you have to first do this and then basically draw the diagram. So this is the diagram that we have already looked into. Okay, Carnot theorem is also important. This actually talks about the law of thermodynamics. This is also very important. Carnot's theorem. It simply says that the Carnot engine is the most efficient engine. Okay, you cannot have any kind of engine which will basically operate between two given temperature and it will be more efficient than a Carnot engine. Okay, that is not true. Okay, that is totally wrong. All Carnot engine operate between same two temperature, have the same efficiency. So if the temperatures are same, the efficiency will be same regardless of the working substance or mechanism. So that means the work done more or less is more or less conservative in nature. It does not depend on the path. If the end temperature and the beginning temperature is the same, the efficiency is going to more or less remain similar. Okay, so this is very important. Okay, so as I said, efficiency is there, and proof we really don't need to do it right now. Okay, and skip this real world engines and all applications. So I'll share this PDF, you can definitely check it. Numerical problem might be, they will ask you to find out the efficiency. They will give you the temperature of the hot reservoir, temperature of the cold reservoir, and then you have to find out the efficiency and you can do your calculations. But please remember that they may not use the term TH and TL. They might tell you the temperature of the hot reservoir is this much, cold reservoir is this much, find out the efficiency. So you'll always see that the temperature of the hot reservoir will be greater than the cold reservoir. If the temperature of the hot reservoir and the cold reservoir is equal, okay, that means whatever heat is supplied, the entire heat is rejected. So it will be nothing but 500 by 500, it will become 0. The efficiency is 0. Quite obvious that heat is not being used by the system or the engine, so you don't have any kind of efficiency for this. Okay, on the other hand, if you see that TH is 500 degree 500 Kelvin. Okay, and the numerator becomes smaller and smaller, that means the efficiency will become much much larger. That's quite obvious. If the heat rejected to the cold reservoir is minimum, that means the efficiency will be very high. So this is maybe something which is there. Okay, so let's say heat rejected is only 100, so that means it will be 100 by 500, so that means it will be 1 by 5, that means 0.2. So 1 minus 0.2, 0.8. So 80% efficient engine, not really possible. Okay, so if you basically consider a Carnot engine model, and we see that the temperature of the hot reservoir is 500 and cold is 300, we get the efficiency of 400, 40%. So it simply means that you cannot have any kind of engine which will basically have an efficiency greater than this if it is operating between these two temperatures. Okay, so this is the idea of efficiency. Okay, limitations we have already discussed. Work done is also simple. We have already looked into the work done process. If we look into the heat given or rejected, basically in adiabatic process, okay, if we consider the two adiabatic process mane, Q heat is equal to 0, right? There is no heat given to the system or rejected by the system, and we know that dW is equal to dq plus du, right? Du. But if there is no heat given to a system, this will basically become 0, and the work done will also become 0, right? There is no work done, okay, because if there is no heat, the work done becomes 0, because we have seen it from the derivations of this. Okay, if you remember, something we've done today, p dv, right? So work done is 0, right? So this part will also become 0. So if the work done is 0, that means for the adiabatic process, okay, for the adiabatic process there is no work done. So that means we have to only take the work done because of the isothermal process. Now in isothermal process, what happens is, initially when we look here, okay, it goes from a volume v1 to v2, that is the initial one, and then when it becomes compression, it goes to v3, and then it comes back to v4. So all these volumes are different, v1, v2, v3, v4. That means you don't have the same work done in both the cases, so that means it cannot be 0, right? So if you basically consider the work done in an isothermal process, which we have seen the derivation already, this is the work done in an isothermal process. So many a times a question might be explain or discuss Carnot cycle, and they might give you, let's say, 12 marks or 15 marks, then you have to derive this work done relation. But if the marks are less, you explain Carnot cycle or Carnot engine itself, that's a very, very long answer. And then after that, when you derive the relation for work done, maybe they don't need the derivation, you can just use the relation for heat, and then directly use it. Okay, so this is Q, which is work done, nRT ln of Vf divided by Vi. Okay, and when we talk about the other part, okay, so we have got two parts. Heat absorbed means you are going to talk about isothermal expansion. We're going to talk about isothermal expansion, and in isothermal expansion, this is my work done, Vb by Va. Always remember this relation, final by initial. So if we look into this graph, here, final by initial, final was at B, so we'll be writing it down as Vb. You can write down V2 also, same thing, and initial is Va, so I'll write it down as Va. Here final is Vd and initial is Vc, right? So Vd by Vc. So this is how we are going to write down this here, or you can write down V1, V2, V3, V4, doesn't matter, more or less the same thing. Okay, so let's get back here. Yeah, so this is QH and RT into TH, Vn by Vb by Va, and for this it will be Vd divided by Vc, final by initial. Okay, so if you want to find out the total work done, you have to subtract this from this, and if you're given a question numerical, you can just take the values whatever is given, subtract one from the other, and then you can find out what is the total work done. Okay, please remember, work done and amount of heat supplied, you're going to get more or less the same relation, because dW is equal to dQ, that's it. Okay, isothermal process, du is 0, temperature is not changing. Okay, don't get confused here, I think I've not mentioned it, but let me just explain this. Basically we are talking about isothermal process mane, heat is this, dq is equal to du plus dw, right? So isothermal processor, there is no change in internal energy, so this is 0. So whether you take dw or dq is the same. So when we derive, we wrote it down as w, but it's an isothermal process, so we can write it down as W or Q. It more or less will be the same. Okay, it's the same, so there is no issues with that. So we can just take the difference between these two, and then you can find out. Okay. Okay. Now this one will not derive. Okay, this is not needed. This is actually how we know that the relation is PV to the power gamma is equal to constant, or why it becomes 0. I have already explained it theoretically. Okay, this is a proof that is being given. Okay, you can use this proof as well to understand this. Okay, VB to the power gamma minus 1 TC VC to the power gamma minus 1. Okay, and what we can do is here is PV to the power gamma relation we have used, and we know that PV is equal to nRT. So in place of P we can write down nRT by V. So we do the calculation, it becomes TV to the power gamma minus 1, right? So in an adiabatic expansion from B to C, this will actually remain constant. So whatever was the temperature here into the volume will be the same as the temperature in the second position or the final position. So TH into VB is equal to TC into VC, but we have used T1 and T2, so you can write it down as T1 and T2, okay, and VB and VC. Then you can take the ratio, you get this relation. That compression also you get a similar relation, okay, and then you see that VB by VC is equal to VD divided by VA. That means there is no change in the volume ratio. Okay, so that means you can basically say that the work done will more or less be 0. Okay, so here we are not going to look into this. Just given an additional explanation, I'll share this file with you. So work done money, I have to just take the QH value and QL value. So this is QH, this is QL. Just subtract one from the other, and then you can find out the work done. So the question might be, what is the work done in case of a Carnot engine? And numerical question. You have to remember this relation. That's very important. Use this. Efficiency already discussed. We can also look into efficiency from a different point of view. Whatever is the work done, that is the output, divided by whatever is the heat supplied to the system. You give some heat to the system, then only it can do some work. So the work done is the output, whatever I need, and heat supplied is the heat given to the system, then only it will do some work, right? But what is W? W is nothing but QH minus QL, whatever is heat given to the system minus whatever is heat rejected to the system. So you can also write it down as 1 minus QL by QH. In other words, we already know that QL by QH is TL by TH. So 1 minus TL by TH you can replace by QL by QH, also going to get the same thing. So you can hold your ears in any direction. Okay, you're going to hold your ear only. So it's the same thing. Okay, कहीं से भी पकड़ो, कान पकड़ने से मतलब है. So it's the same thing. What? So different ways I've already given. Okay. Next we basically have is some numerical. Okay, and we're going to talk about the first law of thermodynamic numerical. We have already seen these problems. Yeah, I've already shown this to you. Okay, this might be there question. Isothermal process में work done क्या होता है? Different parameters, but you need to remember this relation. That's it. Okay, and you should know what are these terms. Okay, 1 mole of gas माने n की value हमें already देवा है 1 mole. So I will just write it down 1 okay, directly. And R we know is smaller gas constant. Most of the times if they are giving a question, they should write down the value. So they will give you the value 8.314. You should remember also. But anyway, it is supplied nowadays. Okay. And T temperature is already given because we are talking about isothermal process. So temperature is fixed 300 Kelvin. So let's put it 300 Kelvin. If it is given in centigrade, please convert it into Kelvin by adding 273, and then only you can use it, right? Volume V2L by 4L. Money final is 4L. Initial is 2L. It is final by initial, so it is 400 by 2, 4 by 2. So I'll take it 4 by 2. So this will be my relation. So I have these values. Just do the calculation. You can find out what is the